What we can say about this machine is this. The UV-Vis Spectrometer will measure the wavelength of radiation absorbed, and by measuring which wavelength are absorbed and which are not, we can gain valuable information on a molecule's electronic structure. So this can tell us where the electrons are, how far apart they are. And this is going to enable us to kind of manipulate this stuff. So the question is, what type of data is produced in this UV-Vis spectrometer, and how can we interpret it? So in a UV-Vis spectrometer, we're going to see an absorption spectrum. So the type of data that we can get is going to look something like this, where it plots absorbance on the y-axis and wavelength in nanometers on the x-axis. So this would be our generic UV-Vis spectrometer. The ones that we're going to use in the lab go from 200 nanometers to 900 nanometers. So it contains a very, very, very small portion of the infrared and ultraviolet spectrum. Remember that the 200 nanometer end is the high energy end, and the 900 nanometer end is our low energy end. So if we said we're going to look at the visible portion of the spectrum, which I'll kind of block off here and use little dotted lines to indicate that. So let's just say here's our 400 to 700. And we were going to analyze our zinc compound. Here we have ZnNH3 6 2+. So the question is, what should our UV-Vis spectrum look like for our zinc? If we have a solution that is clear or it's colorless, are we going to see an absorption in the visible spectrum? Now, you guys are shaking your head no. That's good, right? We are going to see pretty much zero absorbance throughout the visible spectrum. So if we look at this pattern right here, which I'm going to draw out here up on the board, what happens is at very, very low energy, the zinc has an absorption which is pretty much zero. Then as we go to higher energy levels, you see this big bump right here. And we can look at this point right here and call that lambda max, which is our maximum absorbance. Notice that for the zinc complex, that maximum absorbance happens outside of the visible spectrum. So to our eyes, we can't detect that any absorbance is going to happen. So there is not an electronic excitation in the visible portion of the electromagnetic spectrum. If instead of looking at the zinc 2+, we look at cobalt 2+, again we have the same type of plot where we have wavelength in nanometers on the x-axis and absorbance on the y-axis. we go from 200 nanometers to 900 nanometers, and we're going to partition off the visible portion of the spectrum. The cobalt complex is a pink type of a color. So what we see in cobalt and zinc is we see the same type of thing at the beginning, where we have a bump out here in this end, then it tails down, and then we're going to see a bump like this in the visible portion of the spectrum. So we have a lambda max, or a large absorbance, that's going to happen in the visible portion of the spectrum. A pink colored complex, we could say, is very similar to red. So we have to look at the complement, and it's going to absorb right in the green portion of the visible spectrum. Yeah?
So even if there's an absorbance that's higher than the one in the visible spectrum, if there's an absorbance in the visible spectrum, that's the lambda max?
Yeah, so, well, you could say there's a the cobalt compound, we probably would look at 2 lambda maxes, meaning it's the maximum of a particular peak. So in some of these complexes, when we look at them in solution, there could be 3 bumps in there, right? Each one of those bumps is going to contribute to the color, because this is being absorbed right at that point. I mean, it's kind of like a broad peak. They're not really sharp. They're kind of these broad peaks, but we want to look at the maximum absorbance, because that's going to dictate which color you're going to see, is where the maximum of that peak is. Okay? So what we have to do in this case is we have to look at these things, and we have to determine, now that we know that these bumps are there, these absorbance peaks are due to electrons being excited. The question now is, which electrons are excited, and how are they moving throughout the molecule? So I kind of gave you a background of the energy part of this stuff. But now we kind of have to go back, and we have to, I said there's 2 things that you should be that you should pay very close attention to. One was the energy of these orbitals, because the difference in energy is going to determine where this absorbance is. Because for this zinc case down here, we have a really, really large bump at a high energy. So our electron, the excitation is going to take a lot of energy. We have to go out in the UV region of the spectrum here. Over here in the cobalt case, we're going to see an electronic excitation in the visible region of the spectrum. And just how I mentioned about the discrete energy levels and the runner going up the steps here, notice that you see flat portions of this spectrum down here, and then you see a bump of absorbance, and then it goes flat again. This is also further evidence that in a molecule, you have these discrete energy levels that you're going to be exciting electrons to. So we need a very specific amount of energy to excite an electron from one orbital of lower energy up to another orbital that has higher energy. Okay? So that's kind of a broad overview of that. But before we start really critically analyzing these energy levels and everything like that, let's kind of take a step back and talk about the other thing that I was talking about, which is the d electron count for the transition metal, because this is going to be very, very, very important.